use the detector in the receiver, optical receiver section, pin diode and photodiode. Then after receiver section also containing the analyzers. It may be optic oscilloscope viewer, or it may be bit error rate viewer, or it may be um, BR analyzer block. Okay, let us see what is some small introduction about the photo detector in optical communication. Okay, here what is the use of photo detector is, it is a device which absorbs light and converts the optical energy to measurable electric current. What is the function of this photo detector is, it absorbs light and converts the optical energy to measurable electric current. Okay, what are the performance parameters? Here, a lot of performance parameters are there in terms of responsivity, sensitivity. Okay, here in this experiment, we are going to concentrate on two important characteristic of optical communication system to check the performance of the transmission system. Okay, for here, Q factor and bit error rate. Okay, this is a common issues in optical fiber communication system. So that we are taking the two important performance parameters, so that we are going to analyze this Q factor. What is Q factor? Means here the Q factor measures the quality of a transmission signal in terms of signal to noise ratio. Okay. Here, in other words, the higher value of Q factor giving the lower probability of bit errors. Okay, so that you are increasing Q factor gives the better signal to noise ratio, and also getting lower probability of bit errors. Okay, these are our objective of to design any type of optical transmission system. Okay. Then next one, the Q factor represent the quality of SNR is I diagram. Last class itself we are analyzed along with the bit error rate. We can also seeing the I diagram. What is I here? Here specifically the Q factor represents the quality of signal to noise ratio in the I format. It is I is a digital signal. Here I being like our human eye shaped pattern on an oscilloscope. Here that is indicated transmission system performance. Okay, so that here the determining the given bits 1 or 0 is a sampling phase with the largest eye opening. Okay, this is the largest eye opening, means this is the best place for determining whether a given bit is 1 or 0 is the sampling phase with the largest eye opening. Okay, similarly, the larger eye opening, the greater difference between the mean values of signal levels for 1 and 0. The greater difference is the higher Q factor and better PR performance is our objective. Okay, here this is the eye diagram. Last class itself we are analyzing this eye diagram, and with this bit error rate analyzer. Okay, here this is the sampling time interval. The barrier, isolation barrier is there. Here is the sampling time interval. In the sampling time interval, it's um, going to analyze this Q factor. What is the Q factor? Is the difference between the mean values of signal levels for ones and zero. This is for one, this is for zero. Ones and zero. Here one is assumed as mu one, and zero is assumed as mu zero. Okay, it is divided by the sum of noise values. Noise is represented by sigma, sigma one and sigma zero. At those values, two signal levels, assuming this noise is Gaussian noise, and the probability of 1 and 0 transmission being equal to the probability of error, that is p of 1 equal to p of 0, that is equal to 1 by 2. Okay, this is the Q factor determining. This is a formula to find out Q factor. Here Q the modulus of mu1, difference between mu1 and mu0. Here what is mu1 and mu0 means? This is your signal levels for 1 and 0. This mu1 and sigma 1, and mu naught and sigma naught. It's shown here. The rising edge is your falling edge. Okay, so based on that, the Q factor is directly related to the bit error rate. Okay, you can see the percentage of bits that has an error relative to total number of bits issued in a specific time by what is the formula to find out PER. Here the formula find out Q factor. Here BR equal to what is the formula for bit error rate, equal to 0.5 multiplication of ERFC. Here ERFC is the complementary error function of Q divided by 2 power 0.5. Otherwise, called as 1 by 2. Okay, here the photodetector which converts optical power to an electric current and bit error rate is the primary metric used to specify the reliability of communication transmission system. The key factor of the channel, it is defined the electrical signal to noise ratio before addition circuit at receiver, and also can be calculated from sampled signal statistic and used to estimate the system bit error rate. Here's some small introduction about pin diode and avalanche photodiode. Just to go through, the already PPDs are circulated through chat box. Here, and this is our diagram. Based on that, you just to drag and drop the component, you make it as one default layout of to study the study and analysis of photodetectors using Optisim. What are the characteristics we are going to analyze is Q factor and gain, avalanche photodiode, photodetector gain. Okay, here this portion has there is an optical transmitter consists of 4 subsystems. What are the 4 subsystems? Are first one is a pseudo random noise, random bit sequence generator, and second one is pulse generator. Okay, in this design we are taking NR reset pulse generator. Here, what is the pseudo random bit sequence generator is the first subsystem, which represents that information or data that need to be transmitted. Then the output of PRBS generator applied to the NR reset pulse generator. What is the NR reset pulse generator? Is non-return to zero. Electrical pulse generator is the second subsystem which encodes the data from PRBS generator using the NR reset encoding technique. Okay, these are first 2 subsystems, and the second one is a MEZ modulator. Okay, what is the use of this MEZ modulator? Is the last subsystem. It is an interferometer device that interfaces between 2 waves. Okay, here laser wave and also your NR reset encoding wave. The 2 waves of the same frequency but different phases. It modulates. It varies the intensity of light source from the laser according to the output of NR reset pulse generator. Okay, I hope now we are understanding very much with this optical transmitter of this experiment. Okay, next one, the channel. Here these are transmission channel. Here in this transmitter channel or optical attenuator may be included. Here in the what is the use of this optical attenuator is the optical attenuator is a device used to reduce the power level of an optical signal. Okay, the next one, the splitter, the common splitter. We here the splitter called as fork. Here 1x2 means 1 input and 2 output. Here also 1x4 also available, 1x8 and 1x6 also available. Based on your requirement, the splitter may be included. Here we need 2 outputs, so that we use fork 1x2. Here the first input photo detector and second one is a pin photo detector. Okay, you can also use the single after attenuator directly. You can connect photo detector and also have, at the output receiver end you connect one low pass vessel filter, and then you analyze the BR analyzer or eye diagram analyzer. Okay, which you just compare the outputs of the both photo detector APD and photo detector pin. Okay, now just you understand this concept. This is your optical transmitter, this is your channel, this is your optical receiver system. The optical receiver having 2 subsystem. One is photo detector and another one is filter subsystem. Here the low pass vessel filter is the second subsystem which cuts off the unwanted higher frequency signals. What is the use of this low pass filter vessel filter is which cuts off the unwanted higher frequency signals. Okay, then finally we are for analyzing the purpose we include both BR analyzer and also eye analyzer. Okay, here in place of BR analyzer you can also use eye analyzer circuit, eye analyzer block. Okay, why are we using BR analyzer? Mean here itself in BR analyzer here itself you can also view the eye diagram. Okay, so that we use BR analyzer. What is a pin photo detector is the avalanche photo detector is the first subsystem which converts the optical signal into electrical form and can provide the required higher bandwidth. Okay, just you based on the circuit, based on the schematic, you just to make the circuit for this one. Okay, then already you know very well in the form of parametric sweep. Okay, here you include parametric sweep, then only based on the iteration you will get the outputs. You can tune the performance. So you can tune the performance, tune the parameters. Also, you can get the quality factor is high, and also getting the BR rate, better rate. Okay, here these are the steps already. Last class itself, the parameters were step. How to select the parameters to iterate the um, parameter using the sweep mode. Okay, just to the based on the procedures, just to follow the procedures you do. First one is the parameter setup, and the next one is the iteration. Don't confuse with this background diagram. This is a previous example. Okay, just to listen the procedure. What is a double click on CW laser, go to frequency and power. You set the frequency and power. In power, you give the iteration value. Iteration sweep mode. Just to select. There are three modes are available in the drop down list. You select sweep mode and then go to power. You set the values are 10 dBm. Okay, you set the frequency as 193.1 terahertz. The next one, calculate the design using different values of input power. Okay, here select the layout menu in the OptiSystem main window. You select total sweep iterations. You select 10. Okay, previous example is 10. Here in this example, you try with 20 iterations. Okay, 20 iterations. Then click the set the value. Then afterwards, return back to the main layout and click OK. Here in this main layout block, just to click the set total sweep iterations. You select 10, then click parameter sweeps. Here you select CW laser and click linear. Here in this manner, linear. Last class also you done, so that I am not repeating the procedure. Just to follow through this, entering the values for all iteration. The iteration values are -10 to +10. If you are giving values, iteration value 20 means you give -20 to +20. Don't forget to click linear, then you select the values. Okay, then this is your objective, this is your output you are going to get. Okay, after the simulation, the optical receivers with APD generally provide a higher SNR for the same incident optical power. Okay, how you can improve the SNR? The improvement of SNR is due to the internal gain that increases the photocurrent by multiplication factor m. There, these are important thing to get the high SNR ratio, to get the lower bit errors. Okay, so the multiplication factor m is the important one. Let us see later. Then the photodetector system is the first one. Is the Q factor of avalanche photodiode. You must get in this type of output. Okay, then next one. This is for Q factor of pin diode. Okay, how we can get. Okay, this is the output. This is for photodetector BR analyzer. This is for photodetector APD photodetector BR analyzer. Okay, here if you click on BR analyzer means it shows like this. And next one. Okay, this is for APD. This is for pin diode BR analyzer. Also, by the use of another layout here in the OptiSystem main window, having the three sessions. First one is the layout section, and next one is the third one is the script section. Okay, here script section also available, and graph section also there. Based on the graph section, you can select maximum Q factor and gain maximum Q factor of these are the figure shows Q factor versus avalanche photodetector gain. Here the receiver sensitivity bit error rate versus your Q factor. In this manner, you just try to get the graph. Okay, just to go through the procedures you do. Then what is the lab task here? Some of the questions you know yourself. What is the default gain for APD? Okay, this is the first question. And next one, also some for trial and error method, you change the APD gain. How to change the APD gain? Go to the noise tab in the APD. How you can go to the noise tab in APD means double click on the APD device. Here some parameters are there. What are the win under the noise tab? Here there are 4 tabs are available. In this 4 tab, noise tab, you select noise tab. Here, what are the two fundamental noise mechanisms? Here, you can get, if you double click on the ABD in noise tab, you will get 4 or 5 parameters are there. In these 4 or 5 parameters, here receiver noise and short noise also present here. How you can enhance with this avalanche photodiode? These are task. Okay, then next one, change the APD gain to 1. Okay, here also double click on APD. That is a double click on avalanche photodiode. Here you can also some option is available to change vary the gain. Okay, here normally the gain is 0. Okay, here you choose 1, 2, or 3 so that you can get the Q factor and I diagram getting clearly. You can get the high value of Q factor and get the um, lower bit errors. Okay, for both systems, not only with the APD and also try with twin photodiode. Okay, here previous one different 10 iterations of the APD multiplication factor starting from the gain to up to 20 steps. Okay, here previous one is minus 10 and plus 10. You just try with minus 22 plus 20 or 2 to 20. In this manner, you will just monitor the evolution of Q factor, and also by using the graph function. By using the graph function, we plot the graph that shows the relationship between the APD gain and maximum Q factor. Okay, this can be done by clicking on the report tab. Okay, here report tab is there. At the time of simulation, we are seeing how to do this. Okay, next one. Also, the second one is a compare Q factor with the APD photo detector system to one with the pin photo detector. Now, what is the optimum value of APD gain? Okay, the next one, so what is some useful insert there? What is APD in optical fiber? How do you measure APD, and what is the different definition of the APD multiplication factor? So just after this is a conclusion of this experiment. Write your conclusion on APD multiplication factor and its effects on system performance. Okay, at the time of observation writing, in this manner you write the observation. Okay, let us see the diagram. Can you able to see the optic system window?
Yes, sir, it is visible.
Okay. Okay. These are as per PPT. These are all your transmitter side. The transmitter, optical transmitter having the 4 subsystems. What is the first subsystem? Is a PRBS sequence generator. These are input bits, and along with the output of this PRBS sequence generator applied to the pulse generator. Here in this example, we use NR reset pulse generator. Here the next one is a CW laser. This is an optical source of this optical transmitter. Here CW laser is your set the values in the form of nanometer means 1550. In terms of frequency means terahertz 193.1, and power you select 0 or 10, just you apply the inputs value. Then is a combination of two signals applied to the emission modulator. This emission modulator output is sent through the optical channel. Okay, here in this optical channel, we include optical attenuator. Why you are giving the attenuator means just you analyze the circuit to give the attenuation to the transmission system, so that an optical attenuator block is included. Then this block is called as fork. This fork is nothing but splitter. 1 to 2 filter. This is a 1 input, 2 outputs. Why are you using 2 outputs means in the same experiment you use both 2 photodetectors. Okay, so that we need 2 inputs. Okay, two output forks splitter. Okay, here in the one terminal you connect photodetector, and another terminal you connect photodetector. Okay, now what you are telling with this parameter setting, here CW already know. CW laser you can set frequency, power in terms of nanometer. I am given here. If you use unit in terms of terahertz means 193.1, and you also give the powers done. Okay, the next one, these are emission model. Here itself no need to change anything. In photo detector, here I will in the lab task there are 4 subtypes are there. Here main, just click gain, we give you the values are 3, are given the values 3. Just you by you give the value 1, 2, and 3 to try to get the clear eye diagram and getting the bit error rate analysis. Performance is clear way. Okay, the next one on the lab task under the noise tab, you see the what are the different types of noises are there. Here, thermal noise and short noise distribution is the important one in this photo detector APD properties. Okay, here in the short noise distribution, here options are available. It's a WMC white Gaussian noise and WMC noise as are there. These are the two um, uh, noises, sources of noises are there in optical communication system. Here thermal noise and short noise, also Johnson noise also there. Here in this manner you just calculate the noise value. You also you can give the temperature values. These are all the values how you can see. In this mean you just click view display properties, view signal data. Okay, here in this version not supported because 7 version. If you are using advanced version means if you select display parameters, the result values means here the values are displayed here. Here the same thing, photo detector, film photo detector, that's based on the responsivity. These are all the performance parameters of this photo detector, film photo detector. Here responsivity and dark current. Here also nice parameters are there, random numbers, generate random or generate sequence. There are more tabs are available. Just you can analyze this one. Here for analyzing purpose, I have the output of this APD and output of this spin photo detector. I am using oscilloscope viewer. What is a spectrum of the optical signal. Okay, then output of photo detector you connected with low pass Bessel filter for both detectors, photo detector and pin photo detector and avalanche photo detector. Okay, the after output of Bessel filter is connected with uh, two diagrams. Okay, here just you compare with this two blocks. Okay, here also you can include eye diagram analyzer for both, BR analyzer for both photo detector and twin photo detector and APD photo detector. Okay, just you run this program. Then one more step, this one. Then layout. Okay, set the total sweep iterations. Previous example you use 10. In this example you use 25, 20 or 25. Just for analysis purpose, I am using 25 iterations. Then parameters sweeps. You select this CW laser. Okay, then click on this one. Parameter sweeps and all. Just you select. If you select frequency and power already selected and simulation click enable. At the iterations you set 10. Okay, based on that, you just give the values and go to this one. Okay, next one. After running the simulation, what will happen? Let's just see. You can see parallel. You can see how many iterations are going on. Okay, now 25 iterations over. Now you can see the parameters where the values are shown here. There is some problems there, so that it can't be able to show this photo data. Here also you can see the noise levels, thermal noise and short noise, and also there. Here you can able to see this input optical transmitter side. You can see the how many iterations, what is the dispersion at our 193.4 terahertz, and what is the OSNR rate. All the things you are given here. This is a high diagram analyzer. After running the simulation, this is for first one. Okay, why you are using okay, there is some the system is hanging. Just wait for something. The same procedure You do make it as this APD photo detector experiment schematic based on the value. Just to drag and drop, do the experiment. You find out the maximum Q factor value for the first photo detector. It is a BR analyzer. First photo detector values. The maximum Q factor is 4. Okay, what is the minimum BR is 1.4, and high it is 2.63. In this manner, just to calculate along with this one. Okay. You can see parallelly at the time of running, you can see the sleep iteration is going on. Here now we can stop 25 because we are giving the layout sleep iteration is 25. Okay, now you can see the bit error rate for APD. This is a bit error rate analyzer for um, pin photodiode. Okay, here in this manner we are getting the output. Okay, these were output for a photo detector with the gain values of 3. Here we are getting the Q factor and is a eye diagram. Okay, based on that you are analyze these values. Is a high of height, is a BR pattern. Okay, here these are output of photo detector, pin photo detector. Also you see the optical visualizer block. You can see for both. Okay, here what is the use of this eye diagram analyzer? It shows only this eye diagram. Okay, it shows the values of each and H histogram and V histogram and minimum BR. This value in this manner we can analyze this P factor and BR rate. Okay, yourself according to the lab task, you change the iteration values, try to get this photo detector diagram is same. Here this high diagram is not showing clear way. Okay, this is your task, lab task. According to the value, what type of values, what types of values are giving to get this proper eye diagram. Okay, just to go through the PPT based on the instruction, try to get the maximum Q factor value. Okay, here Q factor value is not getting. This is your lab task because for your understanding purpose, for your to test your knowledge, to test your potential. Based on that, we are giving this type of lab task. Okay, this is our output of photo detector. You have to get this VR graph like this, Here there is some noise, there is some um, disturbance are the dispersions are there. Okay, try to get this type of output for pin photo detector. Okay, where your choice, you double click on a photo detector. Here noise is there. Okay, here there is some modifications are there. Just based on that, you just modify the values, apply the dark current values or responsivity values. You change this mode to uh, sleep mode or normal mode. In this manner, you analyze the circuit, try to get the better maximum Q factor for this photo detector. Okay, then another one is another graph showing at the time of discussion. This is a comparison between Q factor versus BAR for this both photo detectors. This is how to draw the circuit. Okay, here just click on view, go to project browser. Here itself the layout is there. Here main layout and report layout and script layout is there. Okay, based on that report, just you insert the graph. here you include this output of this photodetector and output of pin photodetector. Just to drag and drop the values, drag and drop the result, you make it as graph like this. Okay, here this is your task to get the Q factor, maximum Q factor of the pin photodetector. Already you got this Q factor for APD. Okay, what is your task is you have to get better Q factor for pin photodiode. Okay, then also you must you must compare the two values. There is a maximum Q factor versus gain for both APD and avalanche photodiode and also we also compare the minimum bit error rate versus maximum Q factor. What is the minimum bit error rate is? You can see the diagram. Here is your minimum BR value. Your minimum VR values here indicated here 1.45964 10 to the power of minus 5. In this manner, you just analyze the values based on that. The report tab, go to the report tab. You just try to get, drag and drop the result. You make it as graph. This is your task. You check. After getting result, you share your screen. You show the output. At the time of any difficulties, you can ask just to do the experiment. Up to this, anyone having doubt means you can ask.
No, sir.
Okay, just to try here. Sai Ganesh, any doubt?
No, sir. I will try, sir.
Okay, you make it as two experiment here for B section students. You just make it as title like this: experiment 6 and 7, characteristic of twin photodiode and avalanche photodiode using OptiSystem. Okay, here you make it as experiment number 6 and 7. These are two experiments are covered in this unit. At the time of examination, you use for we are asking the first one. Asking for the avalanche photodetector means here no need of this including fork. After attenuator, you just connect photodetector. After photodetector, you connect any type of low pass filter, Bessel filter, or Gaussian filter. Here, according to your requirement, you include this include the subsystem for optical receiver sections. Okay. Another question is here pin photodetector means you don't use the fork block. After attenuator, just connect pin photodetector, just compare the maximum Q factor and bit error rate. Okay, these are so that we called as experiment 6 and 7, characteristic of pin photodiode and avalanche photodiode using OptiSystem. Okay, can you do the experiment now?